Hello, welcome to the another video of the Power Electronics. In this video, we'll have a discussion on the various output voltage that we will get by firing at an angle of 0 degree, 30 degree and 90 degree. And we will also consider the case of freewheeling diode and without freewheeling diode. And before that, what are the equipments here? Let us have a discussion on short description on that. So here we have a three-phase supply voltage, and apart from that we have a switch over here. This is called triple pole and single throw. TPST, we can say this is triple pole and single throw. And then we have an auto transformer which consists of three numbers of single phase variac, and these variacs are each of having a 10 ampere and 50 hertz is the frequency, and the input voltage is 240 volt maximum, and the output voltage in each phase is around 0 to 270 volts. That is possible because there is input is tapped at some percentage of here and not at the fullest, and the output can vary from 0 to 270 volts. So this is what the auto transformer. Then we have a delta star transformer. In the delta star transformer, this is also isolation transformer of the rating of 2 kVA. And the voltage is 440 volt. The winding voltage, maximum voltage sustain is 440 volt at this delta side. And at the star end it is 200 volts between R and the neutral. So we can calculate what will be the line voltage according to rating. This is the maximum rating of the delta and the star end. Then we have a three-phase rectifier. It consists of 6 numbers of thyristor. There are also the diodes on here. If we go for a semi-controlled rectifier, then we will need 3 numbers of diode at the bottom. Then we have a freewheeling diode to freewheel the energy stored in the inductor, and the load we are having a resistive as well as the inductive load to see what is the output voltage, unidirectional voltage that we will be going to see. Also we are going to see what is the phase voltage here, VRN, and what will be the line-to-line voltage, that is VRY. That is the two important things between the line we will be going to see here, and that is between the phase, because what is the input phase voltage to the rectifier and the input line voltage to the rectifier, these are the two most important parts to decide how the output voltage look like. And apart from that, we can say that whatever the voltage across the star winding phase voltage same will be in the delta end, but the delta end the voltage will be called line voltage because whatever the voltage across this winding will be the same as the voltage across the line. In delta side the phase voltage is same as the line voltage, and this RY which is here. And we can also see that this line voltage is also same as the input voltage if this tapping is at the 100% or tapping is at exactly the same at the input and output is same. Then this RY is same as the input voltage, and also we have here the neutral point, and we can also see what is the VRN, the phase voltage over here. That is also important because this whatever the phase voltage is over here, this is actually applied to the control circuit of the firing angle for a 3-phase converter box. So RYB, the same supply whatever here is, that is being supplied from here with a neutral which is also connected to the control circuit, and this R and N that is act as a reference to generate the pulse T1 and for T1 and T4. Similarly, Yn, the phase voltage Yn is responsible for generating the pulse for T3 and T6, and the phase voltage Bn is responsible for T5 and T2. The nomenclature can be T1 in this fashion, T1 and T2 over here, or in one leg we can say T1, T4, T3, T6, T5, T2. However, we can also give a nomenclature like T1, T2 in one leg and write same here T1, T2. So it's up to the user. You can write the nomenclature as per your wish, but if you write in this way, there is a pattern over here. You can get a pattern while seeing the output voltage waveform. So this is what is a circuit diagram, and as we have seen that this is the most important part here is the phase voltage which is get into the three-phase variac, and the line voltage which is being given to the three-phase variac. These are the two most important points. And also the phase voltage which is giving supply phase voltage, that is also very important because that is what responsible for generating the pulse to the thyristors in each leg, and they are independent of each other because of the phase. R phase is controlling T1, T4, Y phase is controlling T3 and T6, and B phase is controlling T5 and T2. And apart from that, we will also going to see what is the load current, what is the load current we will observe, and also the current which is in R phase in the input to the thyristors, so that we will be seeing the IR. And apart from that, we will also see, because this IR will be reflected from here and the same over here, IR, this is the phase current in the delta end. The same what is the line current is the phase current delta end, and the current which is over here, line current on the delta side will be different, and that will be same as the input current. So we will also be seeing what is the IR in the supply side, what is the IR to the inverter input. So we will be seeing these three currents, and apart from that we will have the VRN again in the same picture, so that we can understand these four things together. And also in the specifications what we have, the transformer is a 4:1. That means if the input in the winding here the voltage is 400, the winding over the voltage over this R and N will be 100 volts. So accordingly this transformer is designed, and this transformer in delta star is placed in such a way so that we will get a leading voltage VRN in the output. So whatever the phase voltage, this line voltage over here leads this phase voltage by 30 degree. That means VRN is leading the supply voltage by 30 degree, and VRY is leading the VRN by 30 degree. In other way, VRY is leading the supply voltage by 60 degree. So this is all what is important, and that is required for the three-phase inverter to get a very good output voltage. So here what we can see here is that the picture 1, we have the firing angle at 0 degree. So these dotted lines are the firing angles at T0 degree. So we are giving a firing for T1, this is T2, and this is T3, this is T4, this is T5, and that is T6. So this picture like T1, T2, T3, T4, T5, T6, each is given, and you can observe here is that T1 and T4, T1 and T4 is being given by this red line at 0 degree and 180 degree, and then yellow line is generating, so T1 and T4 because of the red line, we can see in the picture that T1 and T4 in the one leg is being generated by the red line, right? And then the yellow one is generating a trigger at T3 and at 0 degree of yellow and 180 degree of yellow, it is T6. So T3 and T6 you can see in the one of the leg generating the T3 and T6, the pulse, and another pulse is get generated at the blue, the zero intersection of the blue, that is T5, then the other side. So it is like we can have a back calculation and we can get T2. So I can write here, one is because of B and B dash, one is because of R and here R dash, then we have Y, here is Y and here is Y dash. So we are getting the output voltage because of R, Y and B independently, and this is at 0 degree. So if I go for 30 degree, you can understand the difference here. The pulse is generated 30 degree from 0 degree, so that is where the pulse is generated. The same T1 is generated after 30 degree. That is T1 and T2, similarly T3, T4, T5 and T6 is generated after 30 degree. And when we say that 90 degree is a firing angle, so the T1 is generated at 90 degree, the T1 is generated, then after 60 degree again T2 is generated, and like that you have got the pulses T5 and T6 so on. So this is how the pulses are generated at different firing angles. And how they are generated, you came to know that because of the R phase, Y phase and B phase, they are independently controlling the firing in the different legs. So now if you have a firing at this is the first waveform that you can see is the supply voltage waveform, and that is what is responsible for generating the pulses. Now what is this waveform? This waveform is the star side phase voltage. The star side phase voltage VRN is leading the supply voltage by 30 degree already. So you can see that it is leading the supply voltage by 30 degree, and apart from that you can see because this phase voltage is the same as the line voltages over here, and this line voltage is root 3 times than the phase voltage. So if this is peak value is 100 over here, so voltage across this is 173, that is 100 into root 3, and that is same as VRN. So you can see that VRN here is 173 approximately, and that is what you can see here, and it is leading by 30 degree. Since this voltage is what we see here, VRN is the same as VRY, only the difference is that we have that in the simulation we have observed this waveform actually, because when we have a step down 4:1, then this VRN will be, this VRY will be divided by 4 to get the value of VRN. Now VRY will be nothing but again root 3 times of VRN. So if we just go in a straight cut, this is, if this peak value is input is 100, here we get a 173, 100 root 3. And same as if this is 1:1, this is same as 173, then this value will be root 3 times of 173, that will be like 100 into root 3, that is 300. So if it is divided by 4, it is like divided by 4 or 4:1, then this 300 will be, for 300 by 4, that will be 75. So let's see here, you can see that this voltage is 75, and this is nothing but VRY. So here we have VRY, obviously this voltage will be VYB, and this voltage is VBR, right? This is the line voltages, and on the top over here is VRN, and here it is VYN, and here it is VBN. What is the more concern is that this VRN is leading by 30 degree and this VRY is leading by 60 degree. And that is what the output voltage is. If it is triggered at 0 degree, it is like starting from here. And this output voltage V0, and here you can see that this V0, we know the formula of V0. V0 is equal to 1.35 times of V line to line, whatever the line to line voltage is over here at firing angle alpha equals to 0 degree. So now this output voltage is going to follow the same, the line voltages. Also we can put that dotted line over here, that is nothing but the inverse of this blue line on the top of it, so that we can understand that okay, this is the what is rectified output voltage, and we will be getting this output voltage reflected, and the name of this voltages will be because this is the reflection of this blue line which is VBR, this will be VRB, and that this is a reflection of the red line which is VRY, so this will be VYR, and this is obviously VRY, sorry, not RY. This will be a reflection of the yellow line which is YB, so BY, Y. So what you can see a pattern here, V R Y R B, Y B Y R, B R B Y. This is the pattern what you can see throughout this three-phase output voltage, and that is what is reflected here. V R Y, V R B, V Y B, V Y R, V B R, and V B Y. So why we are explaining all those things? So here at the 0 degree we can see that okay, this is 0 degree, that is why it is starting from here. That means it is following the line voltage at 60 degree and it is following the phase voltage at 30 degree. That is the most important point to remember. The output voltage is following the phase voltage at 30 degree and following the line voltage at 60 degree. That is the most important point to remember. And the output voltage, what you can see here, RY, is actually when R is, red line is the peak and yellow is at the least one, right? It is saying R and Y. So here red and blue, because red is at the high and yellow is at, blue is at the bottom, RB. Similarly Y and B, because yellow is at the top and blue is at the bottom, YB. In like that, it is like every phase it is taking the most positive and the most negative and getting the output. In short, the output voltage is following the line voltages. Now, when we have a firing angle shifted to 30 degree, right? 30 degree we have a firing angle. So till 30 degree there is a back. It is like back. It is following the previous voltage. After 30 degree only, it is going to follow this VRY. So VRY is followed after 30 degree only. And the same thing happens to VRB also. See, the VRB is no longer started from here. Rather, it is being, VRY is being followed, and after that, after 30 degree, after 60 degree, right? So this 30 degree firing angle. So after 30 degree from here, or you can say the gap is still 60 degree between each firing angle. T1, T2, T3, T4, T5, T6. They have a gap of 60 degree each. So again after VRY, the VRB is followed after 60 degree, and because of firing angle of 30 degree, this is being delayed by 30 degree again. And in the same way, all are delayed, and what we can see here in the output is because of the firing angle of 30 degree. Now the same thing, if we have a firing angle of 90 degree, then we get delay of the 90 degree from the beginning, right? And after that, the same thing, T1, T2, T3, T4, they are in a gap of 60 degree each, and we are getting the output voltage. This output voltage is zoomed up over here, that is 35 we are getting here. So it is going to follow RY, like after 90 degree it is going to follow RY. So that is why we are getting the very less output voltage in this process. So again, as we told that this VRN is the most important part, the input phase voltage to the three-phase inverter, and VRY is the input line voltage to the three-phase inverter. And then now we will take this VRN as a reference, and at the 30 degree of VRN, the 0 is there. 0 means the output is being followed. At the 60 degree of the line voltage, the output is being followed. Now, if we have this phase voltage VRN as a reference on the top, VYN and VBN, this is the phase voltage which is to the inverter is being there. At the 30 degree of the phase voltage, we know that we get the output voltage, and since the resistive load, this current will be the like this is output current will be the same as the output voltage divided by R for a resistive load, and we get the same pulses over here. And what is interested in this picture, what we are interested to know is the value of the IR, what is the phase current that is being given to the three-phase inverter, that is drawn by the load, the phase current that is drawn by the load. So in the R phase, this is going at like for 120 degree, the R phase is high, and again for 60 degree, the R phase is 0. And again for 120 degree, the R phase is minimum, that is negative current is flowing. Again for 60 degree, the R phase is 0. So this is what the phase current, and what is the R phase supply current look like? The supply current is not so discontinuous, rather it is made little bit of sinusoidal by the help of delta star transformer, and we can get a little bit of sinusoidal in the output like this. So this is what is the For 0 degree firing angle, we have got the phase voltages, current, three currents. So you can see these three currents is the output current, what we talked about. We have here the phase current, IR, what is being drawn by the load, the phase current, and the supply side phase current, or the supply side line currents that is being drawn by the load, that is reflected over here. So now, if the firing angle is now 30 degrees, right? Then obviously after 30 degree only the IR will be reflected after 30 degree only, and then we get this type of waveform for 120 degrees, and it's like a lag by 30 degree. Then we have a zero current for the 60 degree interval. Then again there is a negative current, and we get the same pattern. Only difference is that here it is starting from 0 degree and here it is starting from 30 degrees. The output current will be the same as the load voltage that we have seen, and here in the supply side we get again a very distorted current waveform, like it's starting from here and again negative over here. So it's like it's symmetric, but it is getting very distorted one. Now if we have a 90 degree firing angle, then after 90 degree we have a positive current, and after 180 degree after that we'll have a negative current, and this waveform is getting very, very distorted and discontinuous. The current waveform will be the same as the voltage waveform, and here in the load side the current waveform is again get distorted because of 90 degree of lag in the output, right? So here we just add here the effect of freewheeling diode. Like effect of freewheeling diode is already there. So here what waveform we have seen, it is because of the freewheeling diode. All these pictures what we see is because of freewheeling diode at 90 degrees. So if freewheeling diode is not there, so we can get a negative voltage over here. So here we get a negative voltage, and that negative voltage is persist for some time because of the inductive load. As long as the load is inductive, so this negative voltage will be there. Load is inductive means as long as the energy stored in the inductor get free will from the diode, or since the freewheeling diode is not there, so energy stored in the inductor get feedback to the source. So there will be some negative voltages during the time interval, because the current is positive and the voltage is negative, so energy whatever stored in the inductor get feedback to the source. And another this picture over here is we can see the currents for the same different cases, like 0 degrees, 30 degree and 90 degree, and with freewheel, and this is 90 degree without freewheeling, right? Without freewheeling there. So these part we have already discussed. And what is discussion to be done is that on 90 degree with freewheeling diode. So with freewheeling diode you can see the current is like this here, and here you're getting the current is there, but since freewheeling diode is not there, the current is supposed to get negative, but still it is negative over here. The current is negative for a certain duration. So what we observe here is that the voltage is also negative, the current is also negative during that the small duration of the output in the absence of the freewheeling diode. In the absence of freewheeling diode, this both are negative here. So this is what is one can check this why these both are negative and where this current power is actually drawn out to be. And here you can see that the output is having the same thing on this side, the same at 90 degree the current is positive, after 180 degree the current is negative here, the same after 180 the current is negative. So the nearly same, only there is some difference in the magnitude. Here the magnitude a little bit less, spikes is more, here the magnitude is more, a little bit off, and here the waveform is quite smooth, here is a little bit off, but overall these waveforms what we can see is nearly same in three-phase rectifier at 90 degree firing angle. Now here we have got two comparisons. One is for the full control rectifier, another is a semi-controlled rectifier. Now in full control and semi-control rectifier, we can see over here is that here the output voltage at 30 degree, we have taken a common case like 30 degree firing angle, and here also 30 degree firing angle. The difference is that here we know that this is T1, T2, T3, T4 and T5, T6, T6, right? And here the firing will be at T1. T2 is not there because the T2 is replaced by the diode D2, so there will not be T2, so there will be T3. T4 will not be there, so there will be T5. So here we are getting a firing at T1, so that's why it is following the VRB or RB, right? And then again we are getting a firing over here, so VRY. So here also we are firing, so VYB, RY, sorry this is wrong, RY and RB, and this YB, and this will be V. Now by now you know the logic, VYB and VYR. Again here you will be getting BR, and again after the firing again here you will be getting BY. So this is what the logic of the output voltage is. And what we can see in the semi-converter, you will get the output for the firing T1. What will be output? The same as VRY. Same over here, VRY will be there. But there is no triggering of T2, right? So when T2 is not triggered, so instead of firing, there is no firing over here. This doesn't exist. This doesn't exist. So it will start as usual. It is supposed to start from here. So it will supposed to start from here like this. So that way we will get a very good cap over here. That is V. RB, right? So VRB will be like on full swing. Now there is also, again a thyristor is there in the T3. So because of T3, VRB will go on continue for another 30 degree till T3 is triggered. Then only we have got VRB. After VRB, since there is again no triggering is there, so after YB, what will there? VYR. So VYR will be there for 120 degrees. And then it will go on continue for another 30 degrees till we get another triggering at T5, and at T5 when we have got VBR, and then again we have got a smooth curve, that is VBY. So what we are finding is VRY is conducting for a very less time, whereas VRB is conducting for a more interval of time. That is, this interval is nearly 60 and this 30. This is nearly 90 degrees of time. 90 degrees of time, this is of 30 degree of time, right? So this is what the differences is. So here you have got, this is, the duration should be 60 and 60, 120 degrees. So they are not sharing the equal amount of time. They are sharing 30 and 90. Similarly 30 and 90, like that they are sharing the time. And if we see the current waveform, there is some differences. This is for the 30 degree, again this is for 30 degree semi-converter, semi-controlled. In 30 degree, the phase current IR is starting at 30 degree. That's fine. And after 180 degree from here, you can get a negative current in the phase current, right? Phase is negative current. You are getting the output for RL load will be like smooth like this. And here also in the input phase current IR, you are getting a very nice waveform in this way, but just still distorted. You're getting a positive and the negative. After 30 degree you are getting the waveform like this. But in semi-control converter, the starting point is here also at 30 degree there is a starting point, but the difference what we get here is, here you can see that this zero interval for 60 degree the zero interval is there. Here only for 30 degree zero interval is there. After that at 180 around it will be going to the negative side. So negative current is more, positive current is less. So that creates unsymmetrical in the R phase. Whereas in full control the R phase current is symmetrical. In semi-control the R phase current is unsymmetrical. The output voltage is quite smoother in semi-controlled with a big lap over here. So one can calculate the ripple voltage over here, ripple current and ripple current in both the different cases. And here you can see the input phase current is a little bit of is distorted. It's like going in this way. It's like 1, 2, 3, 180 degree. It should be a 180 degree lag, but again there is, you find there's unsymmetrical in the input current. It is for 120 degree it is positive, then for others 30 degree also positive. So 120 plus 30, it is nearly 150 degree, it is positive. And that side 180 plus 30, that is 210 degrees, it is negative. So that creates a little bit of unbalance in the supply side, unsymmetrical and unbalanced, and that will be that what we observe in the full controlled and semi-controlled rectifier. So this is all. Thank you very much. Hope you have understood clearly that what is the difference between fully controlled and semi-controlled for the voltage waveforms at 30 degree interval and the current waveform. That differences, you can see that unsymmetrical has been observed in the semi-controlled rectifier. These differences are there because of semi-controlled. Again, we have also gone through that for the without the freewheeling diodes. We get the thing is that we get a negative current as well as the negative voltages over here, and that is what the differences that we have observed. And we have also seen for different firing angles like 0, 30 and 90 degrees and 90 degree with free. This is with freewheeling diode and this is without freewheeling diode. And we have observed the currents and voltage waveforms and understand this. Hope anything in doubt you have, still you can write in the comment section. Thank you very much.